Greetings, good afternoon, and welcome to another episode of the Cosmic Pie. I'm Robert Moore, and Wayne who's normally here with me, is feeling a little under the weather. So on that score, we've got Professor Dean Smith with us again.
Back again.
All right.
So my third time here.
Third time, right. So hopefully we'll have a great show for you today, but first things first, we need to do a little disclaimer that the opinions expressed in this show will be those of myself and Dean, not reflective of the University of North Dakota, the College of Arts and Sciences, the Department of Physics and Astrophysics, so forth and so on. I also will note that we do have a live chat, so if you're tuned in and listening to us live, by all means, join in the discussion and put your comments in there, and we'll get to them as soon as we can. Ask questions. We love questions. And on that subject, I guess we'll get straight into things. And we're going to start off talking about the summer sky, right?
Yeah. So
okay.
I guess I've been kind of doing a theme when I when I do my appearances. So first episode I was in, I think that was episode 8. I did the winter sky.
Yep.
Episode 11, I did the spring sky. So
and now 17, let's do the
summer sky. So,
so looking at the summer sky, this is again from Stellarium, right?
This is from the Stellarium, and this is free software. So, recommendation if you want to learn the sky and learn where things are. I only talk about a handful of of objects. So. Now, normally I would do this on the date we're talking, but I did fast forward this. So this is actually a month from now. This is July 4th at about 11 p.m. And so we get a little more deeper into the summer objects that way. And so so right now, if you go out in June, these will be off a little more into the east than what they're showing here. So, and I wanted to show also the kind of time when the Milky Way is out. So right now, you kind of have to wait a little bit for the Milky Way to come up. But in July, that's a really good time to see that. And that is one of the main things to look at in the summer sky. It's also one of the things most people have never seen.
Right.
So
you've got to be in a pretty dark sky to go. And to do that, I've been out to a couple of places around here in my 2 years here in North Dakota. I recommend if you're in the area, Kelly Slough, or go out to someplace like Inkster.
Or Turtle River State Park.
Turtle River, yeah.
But yeah, Grand Forks isn't a big town, but it's big enough that the light pollution, you cannot see the Milky Way.
Right.
Most people who live in any size city cannot see the Milky Way. This would have been a very common sight before electric lighting.
Right.
And so it's a fairly recent phenomenon that most people aren't familiar with this. And so if you do go out in July, you look in the south, if you're out of town in a dark sky, you'll see this milky glow, right? The Milky Way is named that because of the appearance in the sky. Seems like a weird name of a galaxy, but it's how it looks to us from our point of view from inside the galaxy.
Right.
And so we see this milky glow rising up from the south. It's best viewed in the summer. You can see there's a Milky Way in the winter. It's a lot dimmer.
It's dimmer.
And
we're pointed towards the center of the galaxy during the summer months.
Yeah, the center is much brighter than in the winter we're looking away from the center. And so it's not nearly as bright. It's a lot harder to see. So the best time is in the summer. So now from our view up in North Dakota, the brightest part of the Milky Way is low in the south, and that is where we're looking toward the center of the galaxy. And that's the brightest part.
It's in the constellation of Sagittarius, which you may hear the supermassive black hole that's in the center of our galaxy referred to as Sagittarius A star, and that's why the center is in Sagittarius.
Right. Yep.
So sorry.
Yeah, so that black hole is in that direction of Sagittarius.
Yeah.
You're not going to see it. So
No,
so
no.
don't try.
Too much gas and dust in the way.
Yeah, we usually use radio or infrared, longer wavelength light. So and that famous black hole picture was in
Radio wavelengths.
So, um, so, and I do want to mention every star you see in the sky is part of the Milky Way. So in a way, you're seeing the Milky Way in all directions. So why do we see this structure where it's a lot of light along this line? It's because the galaxy is kind of flat. It's about 1,000 light years thick, but 100,000 light years wide. So it's a lot wider than it is thick. So, and the galaxy itself, notice I labeled a bunch of objects in here. Most of the objects that I labeled are in the Milky Way.
Inside of it.
The Milky Way is dense with star clusters and nebula.
And that's why you see that band of milky light of thousands of stars. We're in that band, but when you look along it, you've got a higher density of stars that's there, and that's why it's brighter.
Right. Yeah, there's just a lot more stars in that direction. Yeah. So there's stars, there's nebula, which are gas clouds. You might also notice there's some dark regions in there. That's not areas where there are no stars. Oh, that's dust blocking our view. That's actually one of the big challenges for studying the center of the galaxy. There's a lot of dust in the way that blocks the visible light. So,
yep. So, things I'll point out on this picture is if you look at the upper left, you'll see a bright star Deneb. And then if you go kind of diagonally down, you'll see another one labeled Vega. And then directly below, there's a bright star in Cygnus, in the Eagle called Altair. And those three make the summer triangle. And it's called such because later into July and everything, if you step outside at dusk, the summer triangle is directly overhead.
Right. And so the summer triangle isn't a constellation; it's an asterism.
It's an asterism.
It's the three brightest stars in the summer sky, and each star is the brightest in its own constellation. And in the past, I've kind of talked about distances, and it's kind of neat. All three of these stars look the same brightness, and Altair and Vega are about 20 light years away, so they're roughly the same distance. And then Deneb is 1,400 light years away, much further.
It's one of the few stars. It's got to be a giant star.
Yeah.
Because I never thought about that, but if it's that far away and that bright, it has to be a giant.
Yeah. So it's about the same brightness as the others,
right?
But much further away, over 1,000 light years away. So when you look out in the night sky, you can kind of think about that. You have no sense of distance when you're looking at the stars.
Right.
They all look the same distance to your eye. But yeah, and so to be that same brightness, but far away, it's a giant star.
It's like the high percentage of the stars you see with your eye at night are within about, I think, 300 light years of us.
Yeah, usually in the hundreds.
Astronomically speaking, they're very close. So for something to be 1,400 light years away, it has to be bright, which generally is going to mean large.
Right. Yeah. So it's a large star.
Yeah.
And so it's a blue giant.
Okay.
So a lot of people don't know that. So,
and that's why when you mentioned it, I was like, whoa, that's something we need to talk about.
So. And so we'll go through some of these objects, and one of the things I want to talk about is M13. M13 is a globular cluster. Notice that's not near the Milky Way. It's kind of offset. Galaxies and other galaxies that we look at have these globular clusters around them. And so even these spiral galaxies, these flat disk galaxies like we're in, they'll have these globular clusters. Basically, they look like big balls of stars, hundreds of thousands to millions of stars packed into a ball. There's a bunch of them in the summer sky. I pointed out M13 because it's kind of the biggest, prettiest one.
It's actually nearly or right at the limit of naked eye visible, if I understand it.
I know you
If
can
you're
see it in
really
binoculars.
dark sky.
Yeah, I think people claim to see it, I've never seen it visually.
I've never seen it. It's like Uranus.
Yeah.
People claim they can see it with their eye, but I'm not one of those fortunate souls.
Yeah, you have to have good eyes.
Absolutely.
It is binocular. I have seen it in binoculars.
Right.
It just looks like a little fuzzball, very small little. It's you can tell it's not a star. It's not a point, but
it's why it's in Messier's catalog of not comets.
right. It was a fuzzball.
It was a fuzzball, so it looked like a comet.
Oh yeah,
but
definitely. At low power, globular clusters will look
like a
comets. You can't tell that they're made up of stars. Even small telescopes, they tend to look like fuzzballs, just bigger fuzzballs. But once you get to about 8 inches or so,
10 inches telescope.
yeah, you start to see stars kind of on the outer parts, and then as your telescopes gets bigger, you can resolve that the whole thing is a big ball of stars. Globular clusters, M13 is one of my favorite objects to look at in a big telescope.
Yes.
So if I happen to have a chance of looking through a big telescope, bigger than 10 inches, M13's on the list.
To be honest, folks, I'm sorry if I would have been thinking. I have from my previous days at a university in Georgia, I have some pictures I took of M13 through a 14-inch telescope, and I just didn't think of adding them. So I'm sorry, I won't be able to show you any nice, pretty pictures of M13.
Yeah, actually, of all the objects, that is the one I forgot to bring a picture of.
Right.
It's
one of
those. Also one of those. It's one of the few objects I think look better in a telescope than pictures.
Okay.
And that's my opinion.
Right.
But most objects are going to look better in a picture.
A picture.
A nebula, you do a long exposure and you get all this nebulosity and colors that you can't see with your eye.
Yeah.
Where something like a globular star cluster, it is a bunch of stars.
Yep.
Right? And a picture might pick up more stars, but there's something. It's one of my favorite things to look at in an eyepiece.
For those of you who don't know, the colors on these nebulae are not added in post-processing like a lot of people seem to think. When we get to the pictures of like the Veil Nebula and M27 and M57, there'll be a lot of color in it. If you looked at any of these objects with your eye, you'd just see a fuzzy patch of kind of greenish light.
Yeah,
it's
usually,
greenish to me anyway.
Yeah, I usually see gray unless it's a bright nebula.
Okay.
Orion Nebula will look a little green.
Okay.
So it depends on the size telescope you're
absolutely
using.
Absolutely. But you won't see the colors with your eye because the cones in your eye, the color sensing part, take a lot of light to activate.
Right.
Whereas just detecting that there's light there is the rods in your eye, and they're actually fairly sensitive. I won't here and this now go into just how sensitive, but they're really, really sensitive.
Yeah, but they're not color sensitive.
But they are not color sensitive.
And so that's usually when you're looking at a nebula or galaxy in a telescope, you're using your rods, you don't see the colors.
The colors. Yep.
So I think I have a little animation, and this will show our solar system in the galaxy, and then we're going to travel faster than the speed of light. So don't tell Einstein that we're doing this. So we're going to travel to M13, and so you'll be able to see kind of the galaxy from inside, from our point of view, and from outside.
All right.
Where the globular cluster is.
Take a look at that. So here we are starting out in our solar system, and now we're zipping along.
And now you see the stars starting to move, and now they're really moving. And now we're outside looking at the core of the galaxy. And then we'll back up and see M13. Now this isn't an accurate representation.
Gonna pause.
Yeah, so we can pause here. We can kind of talk a little bit about this. So this is a computer simulation of M13. It's actually roughly what it looks like in a telescope.
What it looks like, yeah.
It's a giant ball of stars. If you were in this globular cluster, you'd have a really nice view of the galaxy from outside the galaxy. Right. Now this galaxy model here, isn't really an accurate model. We think our Milky Way galaxy is a barred spiral, and so I don't see a bar here really. So that's probably the main thing that's wrong.
Right. And nowadays they're beginning to think that in fact it's a two-armed. We're actually a two-armed barred spiral galaxy.
Oh, okay.
So that's a recent development in our understanding of how things are arranged. And people are like, well, how do they know that? And it's again because we use radio to look at and gauge the distances to these stars, and we can then feed that information into a computer that will make a model, an image of it. So we have reasons for saying these things we say, folks.
And the hydrogen gas emits radio waves.
Right.
Even just the cool hydrogen gas, it's not
It's got a
much.
temperature that's above absolute zero.
So-
it's giving off radio waves.
And so we're able to map out, but it's not an easy thing to do to map out from
Oh,
the
no.
center. That's
Oh, no.
why we still learn things about the structure of our galaxy. So if you look close at this image, you might see some other little fuzz balls. Those are other globular clusters.
They look like bright dots.
Yeah, they just
Good
kind of
image.
look like dots here. And so if you see things that look like stars that aren't part of that M13 globular cluster, all those other little fuzzy blobs, those are other globular clusters. So there's swarms of these around our galaxy, and they're centered on the center of our galaxy. They all orbit the center of the galaxy just like the sun and the other stars do, except they're orbiting not in the disk. And so some of these will pass through the disk, and they'll go underneath and then back up again.
Right.
We do see these around other galaxies. This seems to be a common trait of galaxies, is these globular clusters. These are pretty old stars.
Right.
We don't see star formation. We don't see young stars in these. The really massive stars blew up as supernova long ago.
Long ago.
So these are an interesting population of stars if you want to study older stars,
Yeah.
Older than the sun.
They are literally the
place.
oldest stars in the galaxy. Because they are still considered in the galaxy, even though they're not down in the disk, because they are in orbit. They are part of the system.
Yeah. So and they, some of these have millions of stars. They might be almost considered, dwarf galaxies, but
I
they are considered
I refer to them as micro galaxies.
micro galaxies. Yeah. But they are considered part of the Milky Way, and they do seem to be a common trait of galaxies. Historically, these were really important for mapping out the size of our galaxy.
Oh,
So-
right. Yeah.
Way back, before Edwin Hubble, saw other galaxies in the 1920s, showed that Andromeda was another
Another
galaxy.
Yeah.
So before that, people thought the Milky Way was the universe, right? That was, if you mapped out the Milky Way, that you were mapping out the universe.
Right.
And we didn't know how big it was. We kind of obviously knew it was flat just from the, that fact that all the stars seem to be in this line. So globular clusters were used. And I think you've talked in other podcasts about finding the distances to other galaxies using Cepheid variables. And so globulars, they use a different type. It was the RR Lyra
Oh,
variables.
Right. Yeah.
And those aren't as bright as the Cepheids, so they're not great for finding distances to other galaxies, but they're nice because they're all about the same brightness. Cepheids had this problem. There was a big range in brightness.
Right.
And then Henrietta Leavitt found there was a relationship between the luminosity and the period. They're variable stars, and that was what let us use them. The RR Lyras are all about the same brightness. We didn't basically just use them out of the box.
Yeah.
And so if you find the distance to one of these, then you can figure out the luminosity. And you find any of them anywhere else, then you can find the distance, right? You know
Right.
how bright they're supposed to be.
Because again, mention it, 1 over d squared, 1 over the distance
Right.
squared, folks. And that's how the brightness of a light source drops off. So if you know how bright it was originally, you can calculate the distance from that to how bright it appears to you. So
Right.
yeah.
Yeah, so way back 1917, Harlow Shapley, not quite as well known as Edwin Hubble,
Yeah.
he basically found the distances to our Lyras in a bunch of different globular clusters, found they were spherically distributed.
Right.
And so then you can work out, well, what's the center of the distribution? It's the center of our galaxy. And so from looking at the distribution of, the distances to these globulars and how they were distributed, he could figure out the distance to the center of the galaxy, figure out where we are in the grand scheme of things. And it worked out to roughly, 30,000 light years we are from the center of our galaxy.
About a third of the way out.
Right.
Yeah.
Yeah. So the galaxy is 100,000 light years across, so the radius is 50. So
I'll take 2/3.
so
I didn't think about that. Yeah, if we're that far from the center, that's a radius, which half of the diameter. Derp.
so these were used to map out the size of our galaxy. That was kind of our first time. And at the time, the idea was, well, this is the size of the universe, right? Because we assumed all those other galaxies were just nebula inside our galaxy.
Right. Well, at the time, that's all they look like is just fuzzy patches on even the best.
Yeah, you couldn't
chemical
resolve
emulsion.
them as stars.
And it's because the bottom line is a chemical emulsion photograph still has a pixel size. It still has a grain size for those molecules. And so it just kind of smeared out the light over those grains, and you couldn't see actual stars in the galaxy with these photographic plates. But now with CCD cameras, where we can get down on the micron scale size, all of a sudden, hey, there's individual stars there. But Hubble, in looking at Andromeda, was able to pick out a few stars, realized they were Cepheids,
Right.
and that's how he determined that, whoa, this thing is a lot further away than what we thought it was.
Yeah, and those Cepheids are large, bright stars.
Bright stars.
So you could see them in other galaxies. And now, of course, the Hubble Space Telescope basically can resolve the galaxy into stars.
Into stars, right.
And James Webb just did that recently as well.
Right.
Resolved a galaxy into stars. So I guess one last thing people might notice, there's some weird patches in the lower right. Those are the Magellanic Clouds. Those are dwarf galaxies that orbit the Milky Way galaxy.
Yeah.
You can't see them from up here in North Dakota. You got to go much further south.
Got to go down close to the equator.
Yeah, to see those.
And I will point out, because we've mentioned that the globular cluster, I've referred to them sometimes as microgalaxies. Dwarf galaxies still contain tens of millions of stars. So they're still an order of magnitude larger than even the largest globular cluster. And that's why there should be kind of a distinction in there, because a galaxy is much larger than even the largest of these globulars. So, but some of the globs are pretty big as far as number of stars.
Yeah, and in fact, M13 is 25,000 light years away from us.
Right.
So
it's nearly naked eye visible.
Yeah. So it gives you an idea when you're looking at that. As far as things in our own galaxy, it's one of the more further away objects.
Brighter. Yeah.
So most things that we see are in the hundreds, maybe low thousands of light years. So with these globular clusters, you see them from tens of thousands of light years away.
Right. Get a lot of stars together, you got a lot of brightness.
A lot of light in there. Yeah.
All right. So I'm going to go back to this summer frame for a little bit, because we're about to switch gears. And we're going to look at some of these other objects, the nebulae. And we're going to do them in groups, starting with groups towards the center of the galaxy, like M16, M17, and M8. And in fact, that's what this next image looks at, is those three.
Yeah, so these are telescope images of those nebula. One neat thing with the Milky Way is there's so many things in there. You can just scan around with binoculars or a small telescope, and you'll find things by accident.
Right.
So you don't necessarily, and you know, the Lagoon Nebula, that's the top one in this picture. That's bright enough you can see it in binoculars.
Right.
And so it's a pretty easy object to find. You can see it in a finder scope on a telescope, and point your telescope to it. So and like Rob mentioned, you won't see the red color. So these will look kind of gray to you. When I look at the Eagle Nebula,
Which is the lower left.
that's the lower left. I usually don't see much of the nebula unless I'm looking in a big telescope.
Right.
I will see that there's kind of a little cluster in the center there. I'll see that star cluster.
Right.
So the nebula is
You're
actually
not wrong. Yeah.
yeah. So you might see the star cluster and not see the nebula in a small telescope. It takes a big telescope. Sometimes people will use filters.
Mm-hmm.
These are what are called emission nebula. So they emit light just at certain wavelengths, and by using a filter that blocks out all the other light except those wavelengths, it makes them a lot easier to see. So you can block out light pollution and sky glow.
And they are called emission nebula because they're also called another type for the very reason they are emitting light, and that is all three are star-forming nebulae.
Right.
These are the birthplaces of stars. These stars are being born here.
Yeah. So these will have young stars, really hot, giving off ultraviolet light, and that ultraviolet light will ionize the gases, the hydrogen. Some of this will recombine. So when it ionizes, that means the electrons come off of the atom. When they recombine, then you get light emitted, and different elements will emit different colors. So the red color here is from hydrogen.
Because one of the colors that hydrogen really emits, a really bright line, is a red line.
Yeah, it's a very specific transition.
Yes.
Now, if you look at these with your eye, you probably aren't seeing the red because your rods aren't very sensitive to the red, like we mentioned.
Right.
They're sensitive to green, and these do give off green
Some
light.
green. Yeah.
It's doubly ionized oxygen. So
Yep.
it's kind of interesting that what you see with your eye is not what you get with the pictures,
Right.
because the cameras will be really sensitive to the red. They'll pick up the red. Your eye's actually picking up the green, even though it probably looks gray.
Yeah.
Unless you had a big telescope, so these are a lot, very bright.
Or a weirdo like me who has blue-tuned eyes. I mean, I sit here and see in the ultraviolet part of the spectrum a little way, but I don't see the red as well.
Oh, okay.
And so I often tell students when I tell this story about how I see the world bluer for one thing, but for the other thing is part of that bluer color for me is I don't see reds. You don't get more, you get different. So my visual range is shifted a little towards the blue.
Oh, okay.
Yeah. I found that out working with a spectroscope one time, trying to find these lines in a laboratory setting and measure them and do it. I was setting up for a lab and that we wanted to do. And what ended up happening is I found, wait a minute, that's an ultraviolet line of Mercury. And I was like, I'm seeing it. Great. No wonder my eyes are going bad. So these are star-forming regions. They're all those big bright stars that look like they're inside the cloud are actually inside the cloud. They're new, young, hot stars. They're giving off ultraviolet radiation, which is heating up the gas, which in turn then makes it glow. And that's why you're able to see these nebulae so well. That these three, I think all but the lower right one, which is called the Omega Nebula or the Swan Nebula, depending on what you're looking at, how you're looking at it. I think the other two are actually binocular. You can spot them with binoculars.
Yeah. So these, in fact, I usually find them in a finder scope.
In a finder scope.
So
yeah.
And so I'll just, if I'm using a telescope manually, I'll find the Lagoon Nebula. That's the easiest. And then I'll just kind of move up the Milky Way from there until I see another fuzzy thing in the finder scope, and that's one of these other nebula then.
Right. And all three of these are towards that bright region of the Milky Way. We'll go back to the summer sky. They're all down here towards Sagittarius, all down. I'm sitting here moving your cursor, and they're in that bright region of the Milky Way. So you are going to see them there. So if you see that Milky Way, that bright region near Sagittarius, you can easily find these guys. Yeah. Now, I will mention there are literally hundreds of these bright emission nebulae in that direction of the sky. So will you see them all? No. But if you're doing what Dean was talking about and just scanning a telescope through there, you will see, oh wow, there's one. I wonder which one that is. And you'll have to go to the catalogs to find out. Because there are a lot more than just these three. So let's go back to the picture of them.
I do want to mention, one of my favorite things to show people is the one on the lower right, and I call it the Swan Nebula, because in a telescope, it actually does look like a swan.
Okay.
And so, in fact, now there's a lot more nebulosity here in the picture, but the brightest part here, there is a swan swimming to the left.
Okay.
So there's a little, there.
Oh yeah, there
the
it is.
neck, yeah, on the left side, and so that bright part, and a good thing, visually you don't see some of the other stuff that's distracting. You just see the bright part,
right? That
is shaped like a swan, and most people see that.
And so I've always heard it called the omega and call it that myself, because if you look at that dark hole that forms the neck of the swan, it looks like the Greek letter capital Omega.
Oh, okay.
In there.
I always wonder where the omega came from, because I've never seen that.
I'd never seen the swan until today,
okay.
until right now.
Oh yeah.
But I'd seen the omega.
Yeah.
And my pictures I've taken of this nebula primarily are focused on the omega.
Oh, okay.
So yes, I've imaged all three of these nebulae at one point or another. The top one is the hardest one for me to. My images of it don't look good. The lower left one, the eagle, is easiest by far.
In fact, the bottom two are pictures that I took. The top one is from Stellarium. I just zoomed in on because I don't have a good image of Lagoon. So I should get one at some point.
The Lagoon, I understand, is difficult to image simply because you can see that there's this bright region and then it fades off. The brightness fades off really quickly. So it's kind of like the Orion Nebula. To get the bright, you've got to really step down the exposure time. But to get the dim, you've really got to step up the exposure time. And so there's this fine edge you've got to walk.
Large dynamic range that you're trying to,
Large dynamic range, yes. That's pretty much it. And these other two, the lower two nebulae, do not have that problem. They don't have the dynamic range on them.
Yep.
And the Orion Nebula is much the same, and it's an emission nebula in Orion, but Orion is a winter constellation. So we'll talk about that maybe when it comes around to the fall.
About it.
I think we did, yeah.
So my first one, podcast,
we did mention it. Yeah.
So,
cool. So then there's this other type of nebula. I'll go back to
we can point out where these are.
Okay.
And these two are also objects I like to show people, public events through a telescope. There's M27, the Dumbbell Nebula, and M57, the Ring Nebula. I often will mention to people, if you got a new telescope and it's a manual scope where you're trying to, and you don't know what to look at, M57 is a pretty easy one to find. It's right in that constellation Lyra, and it's about halfway between those two stars. You can see in the picture there's one on each side.
Right.
So you point your telescope about halfway in between there, move your scope around a bit, and you see a little donut, basically.
Yeah.
Like a little
donut in the sky.
Little gray donut in the sky. It's bright. If you're new to astrophotography,
it's an easy
you can get
target.
a nice color picture in like 10 seconds.
Yep.
I mean, it does not. You don't have to track. You don't have to worry about your telescope tracking and stacking an hour's worth of pictures. So it's kind of a quick result It's kind of a nice first object to point a camera at as well.
It was my first object to point a camera at.
So, yeah. so you can give you an instant result, and it's kind of nice to get something colorful quick. So.
Yep.
So we can go to some pictures. Now, why are these separate? They're nebula, just like the other nebula.
And
Nebula is a gas cloud, and these are gas clouds, but these are a different type. The other nebula where stars are forming, these are dead stars.
These are where dead stars are dying. Yes.
And so this is what we think will happen to the sun in 5 billion years.
If you're standing about 400 or 500 light years away from the sun, this is what the sun will look like.
So, in fact, I do have the distances here. The one on the left, that's the Dumbbell Nebula. That is about 900 light years away. The ring, that's the one on the right, the Ring Nebula. That's almost 3,000 light years away. It's actually a lot further. So it's a pretty, good distance.
These are visible from a long way off. If you were up here close to them, you actually wouldn't see them.
Yeah.
That's always a neat thing I like pointing out to people is if you were real close, they're too diffuse. You really wouldn't see anything. But if you're far away, the density is enough greater than the background that you can see them against the background.
Yeah, if you're in this stuff, it's really low density gas that's glowing here.
Right.
It's not like, Star Trek, they go into a nebula and suddenly they can't see anything.
Right.
So you probably wouldn't even notice.
One of the many problems with the science of Star Trek, I still recommend the show highly, but, one of the many points where it's like you got to suspend belief.
Yeah. Nebula probably aren't all that dangerous to go into.
Right.
They're very low density. This is like laboratory vacuums on Earth.
Right.
Now,
I want to bring up the colors again.
Oh, yeah.
Because especially the one on the right, the Ring Nebula M57, you see a wide range of colors in there. And they each tell us something and mean something about what's going on in that nebula. So I always like pointing out, we've again mentioned the red. The red comes from hydrogen gas.
Right.
The yellow comes from helium and nitrogen.
Oh, yeah.
They give off a lot of yellow colors when they reionize, when the electrons fall back into the orbits around the atoms. And then the green, as we've mentioned.
That doubly ionized oxygen.
That's doubly ionized oxygen. So in these nebula, you can actually see, we mentioned that stars go through hydrogen, fusing hydrogen, and then they'll fuse helium and oxygen and nitrogen and so forth. And that's about as far as these low mass stars that form these planetary nebula go. And when they puff off that atmosphere, you see the hydrogen on the outside, the helium and nitrogen on the inside, and then oxygen towards the center.
Oh, yeah. Yeah, so you see a lot of that green from the oxygen on the inside. So we probably should talk a little bit about what's going on here. So so this is the end of a star. And I don't know how much you've talked about this in other podcasts, but
I think we've mentioned that it's the end of a low to middle mass star.
Right. So it's a sun-type star.
Yeah.
Basically, that core, once it runs out of fuel, and the fusion stops, you basically have carbon-oxygen core. It starts to shrink, and there gets to be a point where there's this electron degeneracy pressure. So this is basically a quantum effect.
Right.
You can't crush that material, the electrons, any closer together, and you get a white dwarf.
Right.
And you can see it pretty good in the middle of M57, the Ring Nebula. There's a white dwarf in the middle there.
You can see it real nice. It's the bluish one that's right dead in the center.
Yeah. And I usually don't see it visually, but it shows up pretty good in pictures.
In pictures, yes.
So that's the leftover. White dwarfs are about the size of the Earth. So it's kind of crazy. You're seeing something the size of the Earth.
With the mass of the sun.
Right, from almost 3,000 light years away.
Right.
And it's close to the mass of the sun. Some might be less, some more, depending on the star.
Right.
Imagine you're taking that sun And now our sun, you can fit 100 Earths across the sun,
Right.
and you're taking that mass, crushing it down to
Into the size of the Earth.
So this is a very dense, very hot. Yeah. What white dwarfs, I think they kind of get overshadowed by the crazier neutron stars and black holes.
Right.
But they're pretty impressive on their own.
Yeah.
And now, so they're very hot. They're giving off ultraviolet, and that ultraviolet light is what's causing the gases around it to glow.
All right.
And so it's kind of similar to those other nebula. That ultraviolet light basically causes the gas to fluoresce, and then we get these different colors depending on the material.
On the material.
So,
yeah.
And here that green, the O3, is a lot more noticeable than it was in those other nebula.
The other nebula.
There's a lot more of it in here, and so.
And again, that's due to the nucleosynthesis and the outer layers being puffed off due to the radiation pressure.
Yeah, and this is the radiation pressure kind of pushing these outer layers off into this nebula.
And how you can think of how can radiation, how can light exert a pressure? Well, think of it this way: if I have photons, light has energy, right? And if it hits something and is absorbed, it's just like throwing a ball or a piece of silly putty at a wall and having it stick. By the similar token, if it's reflective, shiny, the light will hit it and bounce away, which will actually impart more momentum to it. So that's the thing. Light carries energy, which means if it's absorbed into something or hits and bounces away, it's imparted momentum, some of that energy to that object. And so from that energy transfer, there is now a force, and force per area is pressure. So yes, light exerts a pressure.
And this is measurable.
And it is measurable, yeah.
Planetary Society launched a solar sail a few years ago.
They did indeed.
To test this idea of using the radiation pressure from sunlight to see if they could use that as a source of thrust.
And I will note, it was a successful test. It does not produce a large amount of thrust. You're not going to go see a trail of flame shooting out the back end of this rocket that's propelled by this, but it would be possible to sail a satellite or a probe to one of the other planets via this radiation pressure from the sun. So it's a neat thing. These are all things we're learning as we go along with this stuff.
So there's a lot of different things that go into understanding these.
Yeah.
Do you know why these are called planetary nebula?
Because originally they looked very much like Neptune and Uranus, so they were thought to be just planets that were out there.
Yeah, that greenish blue light from oxygen, well, that's a lot like the greenish blue color of Uranus and Neptune. A lot of these planetary nebula are smaller. These are some of the bigger ones. A lot of the planetary nebula
are really tiny.
Yeah, they're very small in a telescope. You need high power. And so they just look like little spheres, little balls that are
blue-green and fuzzy.
Right. So so they look planetary as a description of what they look like. They have nothing to do with planet formation or anything like that. So a lot of people get that idea.
And that was known. I mean, they knew that these weren't actually planets.
Right.
But they looked
like it.
How do you describe them? Well, they look planetary.
Yeah.
So that's where the name comes from, yes.
So, and there are all these different shapes. Obviously, the ring nebula is obvious. M27 completely, I think it's more like a bow tie than a dumbbell. So you do get these different shapes, but quite a few are somewhat circular.
Yeah.
They have that look to them. So.
And I understand that it may be that most of them look like the dumbbell. It just happens if you were looking at one of the lobes of the dumbbell pointed towards us, it would look like the ring.
Right. So a lot of them we think are like hourglass shaped.
Most of them we believe are hourglass shaped. And that's because not much material comes off of the pole of this dying star, but a lot of it comes off at the equator and spreads out in a nice bow shock. So, that's kind of a neat thing about it all, too. And we mentioned the white dwarf in the M57, the Ring Nebula, but you can also see it in M27. It's that bright star right in the center of M27 is the white dwarf for that particular nebula. So these are neat too.
So these are the kind of the two, brightest, easiest ones, but there are a lot of other
Yes.
planetary nebula.
I've found a few by accident shooting open clusters, what are
really?
called open clusters of stars, and there's quite a few little ring-like nebulae
Like in the cluster?
in the clusters.
Yeah.
So, open cluster, for those of you who don't know, are clusters of stars, groups of stars that are in the disk of the galaxy. Our sun is thought to have once formed in an open cluster because, as we've mentioned on the show, these star-forming nebulae are huge and form hundreds, thousands of stars, not just one or two. And so these form open clusters of these stars. The open clusters drift apart because they're not gravitationally bound. And so we think that the sun was once part of one of these open clusters. So anything more about planetary nebula?
I think we can move on from the
Okay.
planetary.
So I'm going to go back to the summer sky because the last object we're going to look at is up in the upper left, the Veil Nebula, which is a nebula formed by a completely different process.
Right. Well, it's another end of star.
It's an end of star. Yeah.
End of life for the
It's-
star.
It's the end of life for that star.
So stars like the sun, you end up with the white dwarf and the planetary nebula. The more massive stars, you
End up
get a collapse into a neutron star or a black hole, and then you get an explosion, a supernova. And so this is a supernova remnant. There aren't a lot of supernova remnants that amateur astronomers can see.
I think the Crab
Crab is
Nebula
the
is
only
the
other one
only
I can
one
think
I can
of.
think of.
So the Crab Nebula is in the winter sky. Veil Nebula is in the summer sky. Neither one is easy.
No.
So
No.
I think the Crab Nebula might be brighter, an easier one
Yeah.
to see. I've seen the Crab Nebula in smaller
You can see it
scopes.
in a smaller telescope, but
The
it takes a
Veil
telescope.
Nebula is a challenge, and this is one where people use one of those filters I mentioned. Even in a large telescope, people will use one of these filters that basically lets through just the O3, that's that doubly ionized oxygen, and maybe one of the hydrogen lines that's right next to it.
Right.
The H beta is right next, these two lines are right next to it. So, in fact, when I look at it, I usually use a filter, even in a large telescope. So this is a challenge. This is a large object. In most telescopes, you are only going to see a piece of this. And so there's this little piece on the right side by that bright star. That star has nothing to do with the nebula, it just is in the way. But there's that piece, and then there's the piece on the lower left. And so you usually point your telescope at one of those two pieces.
Yes.
And you only get one of those two pieces in the telescope because this is a large object.
And to really see it, you're doing a 30, 60, 120 second exposure in a camera.
Yeah.
So
you're
not seeing this with your eye.
Yeah, this is a challenge. You do get a nice view if you can look at this in a 10-inch or bigger telescope with one of those filters. You can get a good view.
That's the thing that I've not used.
You
one
haven't
of the
used.
filters.
We're gonna have to get you out look at this with a filter. Yeah. Just a 12-inch telescope with a filter.
Yeah.
It's actually a nice looking object. It goes from a challenge, I can barely see this, to actually seeing some of the structure.
Oh, beautiful.
Yeah, it's actually really nice object.
Like I said, it was hard to do just with a camera.
Yeah.
So
this is a nice object if you have the right telescope and filter to look at it.
Right.
But it's not you can see it in smaller telescopes, but there's a challenge. You're just happy that you can see it.
Right.
So
right.
So it's believed that this is a supernova remnant. This is the remains of a star that blew up. I believe this is like 100 light years across. So this is
it blew up a long time ago.
This is like 10 or 20,000 years old.
Yeah.
The numbers, there's a lot of variation depending on where you look and what the recent information is, but it's believed that this was a neutron star, but that's never been found. We've never found the remnant neutron star for
neat.
this.
Okay.
So unless there was some news that I missed,
Yeah.
so as far as I know, we have not found the remnant neutron star for this.
And people
So-
would question, okay, well, why wouldn't it be just in the center of
So
the
yeah,
cloud?
so there's a
And the answer is you kick off a big explosion like has created this, and what's going to happen? It's like throwing one marble at another one real fast, real hard, so that it kind of explodes apart, and the star shoots off in one direction, and the remnant kind of drifts apart in
yeah.
a
So
circular
yeah, there can
fashion.
be a kick where these things
Yeah.
travel. So it might not be in the center. The other thing is neutron stars are really hard to see
Yes,
unless they're pulsars.
unless they're pulsars, and pulsars pulsate because they give off beams of high energy
Right.
light,
But just in two directions.
and just in two directions. Yeah,
So if it's not crossing our path, we don't see it.
we don't see it.
And so, yeah, there could be a neutron star. Just because we haven't seen it doesn't, that's
It's
not really
there.
a problem. They're really hard to see
Yes.
unless it happens to be lined up right as a pulsar. So,
Yep.
um,
So that beam of light at either pole comes out at us.
yeah. So that'd be really cool if we found the neutron star.
It would.
But I'm sure it's there somewhere.
Yeah.
So, but this is a neat object and to look at. This is the remains of a star that blew up, and again, it's emission lines.
Yep.
Now here, there's no ultraviolet light from a nearby star. It's just really hot because of this shock wave.
That
Uh,
blew through it.
yeah, and so it just happens to be really hot from that. So and you do get these different emission lines from the different elements. And
Right.
lucky for our eyes, doubly ionized oxygen is in there,
Is in there.
and that just happens to be our eyes
Are
see that
sensitive
easy.
to it,
So so that's usually what you're going to see if you look at this visually.
For reference, for a red light to appear as bright as a green light to your eye, the red light has to be about 500 times brighter.
Oh wow.
And for a blue light to appear as bright as a green light, it has to be around 1,000 times. Our eyes are actually very insensitive to blue and fairly insensitive to red. But green and yellow, oddly enough, where's the peak of the solar light that
right.
gets through the
Yeah,
atmosphere?
right in the green there.
Right in the green-yellow band. So our eyes are designed to see what the sun is primarily putting out.
Yep.
So
So
everything else is just there.
yeah, we're just lucky that this one form of oxygen emits light
Right where we can see it.
right where our eyes are sensitive. Otherwise, these would be even more difficult to see.
Yep.
I mean, if it was just that red hydrogen light.
We wouldn't see it at all. Yeah. So, and you mentioned that the gas is hot due to the shock wave, even though it's probably about 10 to 20,000 years old. And people go, well, space is cold. Why is it cooled down? And the answer is because the only way it can cool down is through radiation, through giving off light, which is the least efficient way of transmitting heat. Conduction or convection are much more efficient at getting rid of heat. So radiation is very poor at getting rid of heat. This is one of the problems with the space stations is they have to allow for big metal fans, big metal sheets to dissipate the heat because it heats up real quick and you can't get rid of it. So the same thing happens with this gas is really the convection, the radiation and the convection of it just spreading out are the only ways it's losing heat. And both of those are fairly inefficient in space. So neat stuff. Anyway, I think I came with another topic that I could have talked about that's completely unrelated to these two, but I'm looking at the time and it's like we've only got about 5 minutes.
Yeah, I'm surprised. I didn't think I'd fill up this much. But
Yeah.
So
Well, it's always good because, you come here with these interesting topics and it's interesting to look at what's up in the sky at our time of year. So I will never complain about that. And just, in fact, my only question is there any other neat little thing you want to point out about these objects? So I'll go back to the summer slide again. For me, the only thing I would point out is that most of these constellations that these objects are in are easy to see. Sagittarius, look for the teapot. It's actually, which is an asterism inside Sagittarius. Right. And you can kind of see it down here in the lower part of the screen, the picture, lower center. It looks like a teapot.
Right. In fact, you can think of the Milky Way as steam coming up out of the spout of the teapot.
Yeah. Altair is a pretty bright constellation. It's one of two that looks like a cross. And the other one that looks like a cross is Cygnus.
Yep.
Right above it.
Yeah, the constellations aren't labeled here, but Cygnus is the constellation that Deneb is in. And then Altair is in Aquila.
Aquila, yeah.
I have no idea how to pronounce these
things. I don't either. I've always pronounced it Aquila.
I had bizarre pronunciations when I first got interested because I was just reading books and I didn't know anyone. And so just made up my own. So I'd say the one challenge is Hercules.
It's hard to identify. It really is.
The way I find it is I find Vega, I find Arcturus, and then I look in between them. And that's right in, draw a line in between those stars, and then you look for that trapezoid. That's Hercules, the body of Hercules.
In fact, that's another asterism. It's called the keystone because it's shaped like that top in an arch, a stone arch.
Oh, okay.
That top keystone, it's shaped kind of like it. And I will note that the other two bright stars in the summer sky are Arcturus, which has been mentioned now over there in Bootes is the constellation, and Antares, which is almost right above due south, the S in this image, and that's in Scorpius.
Right. Yeah, I forgot to talk about Antares. Antares is a red supergiant.
A red supergiant.
It's kind of like Betelgeuse. Betelgeuse is in the winter sky. Antares is in the summer sky.
Yep.
So if you missed Betelgeuse, you want to see a red supergiant. Antares is out
Antares
in the summer.
Yeah. So on that note, I'll go back to looking at us, and I will leave you like Wayne normally does with a quote. This one is going to be from an author as opposed to a scientist, but I like the quote. So here it is. John Green says, "What I love about science is that as you learn, you don't really get answers. You just get better questions." And on that note, I will say good afternoon to everyone. I hope you enjoyed the show. I hope to see you again. And if you're interested in science, please consider the University of North Dakota. In particular, consider us, the Department of Physics and Astrophysics. So anything else from you, Dean? Any other thoughts?
Can't think of anything. So
all right.
Have a great day.
Have a great day. We'll see you next week.